Okay, and we are live. So today's a live sound session. We're going to be discussing spinal graphs some more, and just in general the concept of advancing the science on hypergraphs in general. And we have a special return of a fellow here, Richard. So thanks, Richard, for being back with us. And Carlos is going to be talking mostly today, and we might be joined by Nick a little bit later. So yeah, thanks so much, Carlos. You can tell us what we're going to be studying today.
Yeah, amazing. So taking the opportunity of having Richard back with us, I'll update on where we're standing in terms of our hypergraph foundations. So just to give a brief context to everyone, let me maybe talk with a notebook on the screen so everyone can see. I guess you can all see that, right? So,
yep.
So yeah, we are in a process of I don't know how to say it, redefining. It's not really the right term, but reaffirming perhaps is the right term. Reaffirming the foundations of hypergraphs as we are going to move forward in implementation and hopefully run some stable code for specific applications, things like that. So as many of you know, we've run hypergraph code before for a variety of things, most notably the physics project and all the effort that went in that direction in the last few years. But with my investigations into higher rarity algebras and higher order mathematical structures, there's been some other use over there more symbolically. And of course, Richard worked with hypergraphs more for sort of for visualization purposes and whatnot. So in the last few weeks, we've been trying to also by Stephen's demand, so to speak, we're working on redefining or reestablishing what the core objects are and what are the really computationally fundamental or computationally primitive objects that we wanted to be working with. And so the main goal of this is, as you can see on the screen, is first of all to account for all the kinds of hypergraphs that you find in the literature. So these are the hypergraphs that everyone's familiar with, the sort of undirected, sort of graph-like, but higher order kinds of hypergraphs, but also typical hypergraphs in the literature include many-to-many edges, include sort of fully symmetric edges, they include partially symmetric edges, things like that. We want conceptual definitions that are clear and that we can all be sort of on the same page. What would they represent and how to think about them? We obviously want the computable implementation of those. So our objects in our backlets and our functions, we want them to have some sort of base clarity and base notions that are sort of held across different instances, and sort of shying away from just finding a particular hack or a particular trick that works for certain things that are very domain specific or application specific. We rather have sort of a general point of view, and in particular, we want a point of view or a paradigm that is very compatible with rewriting, with the notion of processing hypergraphs with this notion of rewriting, and using the multi-way graphs and the causality analysis of the rewriting systems and so on. The conceptual summary goes as follows. And Richard, please feel free to stop me at any point if you have any sort of comment or pushback or something is unclear. I should say in advance that some of these definitions are still being discussed in exactly what they are going to mean, but hopefully this will give you enough of a spirit of the definition that it's clear enough. So the first point is we begin by our primitive elements. These are the nodes. So something like the nodiverse is the collection of all these things. It's a virtually infinite set of all the nodes that carry this unique identity beyond their individuality, as I said here. So these are featureless things. They are well understood as, or better understood as, memory addresses. So essentially places where you can deposit some data, and essentially a deposit for some data, some symbolic data. Now, you want to essentially build data structures on these things. So you want to be able to group them in some way. So in this fundamental notion of there are discrete bits of information out in the world, and what we do as cognitive agents or computational agents is to sort of bind them and relate them, establish some interaction between them, and sort of record that kind of interaction. So the first primitive notion between nodes is what we call a bag, which just to call to the usual notion. Maybe we want to call this bonds or something a bit more abstract than bag, and we want to reserve bag to the actual data structure of a bag of symbols or a bag of pieces of data. But in any case, this refers to the comprehension of a bunch of nodes, right? So it's just basically delimiting this bunch of nodes. This is what I'm looking at. So some finite subset of nodes in this.
What about the body? Like the body contains all the bones and the spines and everything.
Just yeah, I mean, as I said, I'm not really like I'm kind of abandoning this sort of anatomical language line, because so I think I'd prefer to bags. I think I'd rather call them bonds. I much rather have the sort of more chemical analogy than the sort of anatomical analogy. I mean, spine is still sort of abstract enough that I think is okay. But yeah, so basically, the bags or bonds just represent that there's a sort of declared set of nodes are related somehow, and this is somehow the sort of the foundation of an edge. This is going to be what it tells you the stuff there exists in an edge, right? The spine. So the kind of data structure that a bag is simply a collection of. So it's just a subset. Unordered. There's no further implication of any sort of structure among the nodes. Now, that further structure is provided by what we call a spine or a spinal graph, which for current applications, we're thinking it to be simply a connected directed graph simple connected directed graph on the nodes in an edge, in a bag or bond. So the idea will be clear in a second why we want to do that. And for now, just consider that there is a sort of a bond or bag that establishes which are the nodes that we are relating, and then there's a spinal graph that gives some relational information or some further relational information between them.
Or you mean directionality? Do you mean it's separating the directionality from the connectivity, or is that?
Yes, actually, yes. That's basically the notion here, that we are.
All right.
We are the broader relational information, which is just a statement of which nodes are related, is the bag, and the internal sequential or more directed or directedness information between the nodes is encoded by the spine. That's essentially the split. It's like trying to be instead of, because so the goal of this, maybe let me focus on spines for a second before talking about edges and whatnot. Okay. So the whole point of this spinal graph business is precisely that you want to, in an efficient way, you want to encode what we called hyperedge symmetry before, which really should be called hyperedge type in a broader sense, in a graphical minimalistic way. You don't want to be dealing with kind of all the permutations that are raising from the ambiguities that, an undirected edge here has a lot of permutations, and you don't want to just say, you have a lot of different iterations of the same thing. So the idea is that in order to, so it's clear in all these examples, right? You have something that is ordered, like, I don't know, you have a notch here to indicate that this is the first element, and then you have a directionality. So you can count like first node, second node, third node, like essentially like a list, an ordered list. You can have a many-to-many edge where you have maybe no internal order between the inputs and outputs, but you do have sort of less input-output nodes or source and target nodes. You have something that might be cyclic, where there's no notion of first or second or last, or anything like that. But there is a sense in which, given any node, you can tell who is the successor and who is the precedent node,
Yep.
right? And of course, there's the undirected, which has no statement about any sort of preferred symmetry or preferred order. And then there are composite things that are not quite any of those. So things like, you can think of these two nodes on the left as being somehow source nodes, but they always come in this particular order: the bottom first, top second, and then both come as an input to the output that is the right one here. So there can be some partial kind of things. So
yeah, that's interesting. I thought about these in terms of like building like graphical programming languages where scroll down please a little bit just to that example where you had the 3 on the left and the 2. So like say you had 3 input, just up 1. Yeah, this directed example is interesting where you might have sort of 3 incoming things which then branch out to 2, but there's a whole like zoo of possible connectivities or meanings that you can ascribe to these hyper edges. And yeah, I guess it's a case of like interpretation, really. Yeah. Oh, that's cool.
Yeah, exactly.
You kind of catalog them. Yeah.
Totally. That's totally philosophy here. So conceptually, what we are meaning to do by separating bag and spine, or bond and spine, is that the bond the bag just tells you, okay, this is the nodes that you comprehend by this edge information, and the spine, which we are currently thinking of as a simple connected directed graph, but it could be something else. You could have even like some nested structure of bags or whatever. Right? Like you could implement it in different ways. For now, we think of spines as directed graphs because it's just easier. I think we just have an easier time.
It's an interesting, like, I guess, factorization of, and I could say from like a implementation standpoint, like once you tick it to a computer, there was an instance where I had introduced this notion of a link, which is kind of, I think I brought it up like many live streams ago or something. It's like where you have a vertex and some edges. Anytime that edge is kind of incident on that vertex, there is some underlying data implied in this notion of a link, which is what joins the vertex to the edge. Like mathematically speaking, it's kind of invisible or implied, but on a computer, you need to kind of you need to store this somehow, whether that be that the vertex is referenced inside some list somewhere, or that there's some extra data structure, and upon which you can apply more data, which can include the directionality or some kind of color, or I don't know. It's like it's really up to you what you put there. So like a vertex incident on sort of multiple edges can have some information that represents the pairing between itself and the edges which are incident upon it. So which kind of gives you a lot of freedom to sort of. But yeah, it seems that we in previous things we want to deal with like multiplicity as our sort of fundamental data storage sort of mechanism, so we don't or not. I don't know.
That actually allows me to segue into what here we define as sort of hypergraphs proper, which is actually populating the bags and the spines and what they sort of specify. So an edge is really like an actual edge information should have both the bag spine structure, which is the analog of a sort of data holder, right? Like like the notion of a data structure, like a list or whatever, a table or whatever you like to think of, and then what we call the memory locus for actual data elements, which we are just going to be thinking of as labels, as some kind of symbolic bits of data. Those are to be populating the nodes and the edges, right? And so edges effectively, in a conceptual sense, they generate new nodes, right? Like the moment that you you create a bag of nodes. You're virtually creating a new node where you can attach information. So this is what in the infrageometry stuff we call the edge place idea, which is very standard in when treating hypergraphs, is that you replace whatever edge by a new node, and then you maybe have a graphical structure around that node. It's kind of easier to parse many times. So in that sense, conceptually, really nodes are this primitive thing, but they can be built in sort of towers of relational structures, which are the edges, right? But generally speaking, the hypergraph will be some kind of specification of such edge data, which is just a bag and a spine together. So a bag which delimits a number of nodes and a spine between those with some labels thrown in, and then that as many finite times as you want to have a hypergraph, which you can understand actually as a further labeling on top of everything, right? Like you could just specify a sort of meta labeling, which is just adding like some extra information to each label, so that is labeled as in hypergraph 1 versus hypergraph 2. So you could have in the same sort of universe of nodes, you could have labeled things that allow you to kind of specify that this is kind of like edges of color blue and edges of color red, and you can distinguish them while all of them carrying their unique bits of data, right? Which is kind of like saying you can have duplicates of the same data structure in your computational system, right? Like you can have a list of cities that is whatever 20 elements long. I can have a list of population numbers that is 30 elements long or whatever, right? And these are both in your computational system equally. There's no confusion there. So that's how we imagine these hypergraphs in general. And so the idea, so of course, is that the way this kind of would look like is you have like the bag of a ternary edge will always look something like this, that has sort of 3 edges bound by some sort of surface between them. Then if you wanted to have something like an ordered hypergraph, then you represent the spine of an ordered set. So in here, the spine is obviously implying some internal total order. That's why we call it ordered. Similarly with cyclic, where there you can sort of create a cycle and actually have no longer a notion of a first and a last. And of course, we can also have this sense of full symmetry, which just means that you have a complete graph, complete directed bidirectional graph on all your vertices. So yeah.
Can I ask about the directed case where you may have two unordered vertex sets given an edge, which would represent some, let's say, incoming and outgoing, partitioned into sort of two groupings, but they don't have any ordering among those groupings. They're just split into kind of 2 categories, arbitrarily named input and output, but it could be anything. Is that covered by? Yeah. So it was exactly the directed case that you had for that 5 edge, which had sort of 3 on the left, 2 on the right.
Yes.
So is that covered by any of these that you? Because in this one, I would say that those vertices are sort of partitioned into 2 categories, but there's no sense of order. I mean, there is a sense of directionality that's implied when you think about inputs coming in and going to outputs, but among the left-hand side vertices and right-hand side vertices, there's no sort of notion of ordering.
Absolutely. And let me just say, Richard, that question is somehow one of the core definitional issues that we are having at the moment.
Okay.
In the sense that, so let me, do I have, I think I had a diagram. Where was this diagram? Oh, I think it was this one, possibly. No, this was just about loops. So, well, in a sense, I can explain with this diagram very simply. So the problem that we have, actually, Wait, no, I haven't. Oh no, sorry. It's let me share my whiteboard for a second because I have it
No
on a
worries.
whiteboard. It wasn't a notebook. Um, so this is a very important question. I can just slightly rephrase it by saying, what is the difference between full symmetry between the nodes and the existence of a complete directed graph between them and the absence of edges. And so if here it is. Let me share it. So this should be loading.
Yeah, I guess I'm thinking, like, does the spinal graph give you some sort of like universal, something that's sort of like universal? Because
Yes.
otherwise we would apply some restrictions like for our purposes, and somebody else might come up with their own definitions. But if it's universal, then that's nice because it kind of caters to everybody, and we all speak a common language, kind of thing.
Yeah, that's definitely the intention here. The intention is to give at least provide a language that I don't know why this is not loading. It might just be a bit of a connection moment. So that's definitely the intention here, that we want spinal graphs to somehow replace not replace, but give an alternative for data structure encoding, right? So with the constraint that of our particular technology stack. So assuming that we have very well-oiled machinery to deal with graphs, like graphs proper, right? Oh, here we go. So yeah, so this is basically the this part is we were discussing in the last live stream when Nick was around in these cases. So there are a few definitional issues that, now that you point out the kind of most difficult of them, I'll go quickly through this. So first of all, it's likely that we want this to be connected because we are likely to want to think of edges in general as just somehow labeled directed subgraphs in hypergraphs, and because I mean, the idea to use directed graphs is heavily motivated by the notion that we could have some sequential information within edges, so that if we wanted to, for example, flow through every node, right, we would want to find paths through nodes and things like that. So connectedness seems like a very intuitive thing to have. It just kind of makes sense, and that's sort of relegating the notion of bag to be actually fully encoded. So the notion of how you delimit a bag, that's just the complete connected component of a directed graph, right? And so it might be something that is for free. I don't think it's super fundamental. I think it will be fine to also have bags that are their own thing, and then we define possibly disconnected directed graphs on top. Who knows? But now the point is, you can have something, data structure that that have pretty different applications, and they're prominent in different implementations. Things like trees, things like tuples and total orders are quite different to things like cycles or things like many-to-many. And so the idea is that related to the question of connectedness, like the sort of binary connectedness, meaning connected or not connected, there's also a question of degree of connectedness, right? And this is basically what your question, I think, was pointing at, which begs the following question. If I have 3 nodes, 1, 2, 3 here, I can imagine 3 situations in which I can clearly distinguish source and target subsets, right? It's clear that in all these 3, most people would agree that 1 is having a source role in a data structure, and 2 and 3 are somehow, or at least some of 2 and 3 are having the sense of a target, right, in this data structure, simply by doing some directed graph analysis, right? So by the directed graph topology, we can just see that the out degree in one so the in degree 1 is 0, and the in degree in 2 and 3 is non-zero or maximum or whatever, right?
Yeah, yeah.
So there's an intrinsic way to tell source and target in both. Now, how 2 and 3 relate is a bit more complicated. It's a sort of richer story, because it's clear to me that you can say that, a directed edge between 2 and 3 implies that within the subset of 2 and 3, I have a spinal graph, right? So I can say that there is a total order, meaning 2 comes before 3. Then it's clear that thing is a tuple, right? It's clear that if I have the notion that 2 goes to 3, 3 goes to 2 in this edges, then I have some sense of cycle, and because it's just 2 elements, that's just like a bag, right? It's like an ordered pair in those 2. But when I have nothing between 2 and 3, which is a perfectly valid directed graph, it seems, some people would think, well, that's like the pair that is an order that I have 2 arrows in both directions. But actually, it's a bit different, because it's the lack of information on how to flow from one to the other, right? It's not the information that you can flow from both to the other. It's the absence of that information. It's not. So to me, this is a. Sorry, I see Nick just connected. Hi, Nick.
Hello. Hey, Nick, thanks for joining.
So it's to me, this is one of the kind of up in the air issues. I don't think it's particularly problematic for anything in particular that we're thinking about very hard right now.
Yeah, it's open to interpretations. One could interpret A and C as being equivalent, but they're not. And you could interpret them as being communicating something. C as being distinct from A, having some meaning, or okay.
Precisely. So I tend to think, and we'll move into in a second, and because last time, just for context for Richard and some of our viewers, last time when we talked about this last week, we're focusing on what spinal graphs could do for us, and that there was sort of the difficult part, and this whole canonicalization problem, and so on, and we didn't focus on what they could do for us. That was easy. That's sort of the advantages that spinal graphs seem to give us, in sort of dealing with hypergraph rewriting and the kind of problems that we are tackling at the Institute. But indeed, this is one of, as Richard said, this is sort of open to interpretation. My current interpretation, I am leaning towards the interpretation that spinal graphs will give us the ability to express some data structures. Like, it's clear that a spinal graph will give us a tuple. It's clear that it will give us a tree. It's clear that it will give us cycles. It's clear that it will give us something like source and target distinctions, because of just, in degree, out degree, 0 values in your graphs and things like that. Like, it's clear that you would have some way of expressing those things, but there are more things thrown in, right? Like, there are more sort of intermediate species that don't immediately have an interpretation for a data structure that is familiar to us. So my understanding is that we want to be somehow impartial towards this. Like, we don't want, like, I would rather not be a control freak of these structures, right? And just like say, hey, I need to have perfect understanding of every single spinal graph and what it means and what it represents. As long as I can have a clear understanding that some data structures are well represented within this class of edge types defined by spinal graphs, then I'm content, right? Like, I don't have to. So in that sense, the distinction, so B has its own entity. There's, whatever, there's a, like, some people might think, I was initially thinking that the B spinal graph should be representing something like source single node into a target tuple, like more or less what is represented below here, right? But you might think, actually, no, why should the tuple be the target when you can't really define both 2 and 3 as target nodes, because the only the only real target node, the only sort of sync node is 3, right? Where the out where the out degree is 0, right? So 2 and 1 have non-zero out degree, and 3 has 0 out degree. So in that perspective, this data structure might look like, you have a clear source, you have a clear target, but you also have middle nodes that are sort of like intermediaries, right? Which you could imagine as it being some kind of modulated interaction, right? Where you have 1 to 3 interaction that is modulated by 2, right? That somehow alters it somehow. So I don't know. This is what I have an open mind about. It's not completely clear to me that that represents a 1 to 2 tuple. But what is clear to me is that you can definitely restrict to families of directed graphs that would very effectively recover your data structures. And this is just to show the final diagram that I had for Richard to catch up on this spinal graph business. Is this thing. So it's just a summary. It's basically, you probably got the idea already, but just to be clear, yeah. So it's basically this diagram, right, where there are clear classes of spinal graphs that recover the data structures that we're interested in, right? So, for example, path graphs, like these things that essentially give you a total order in your nodes, should clearly represent tuples. Cyclic graphs, which are just cycles, n cycles or whatever, give you cyclic data structures. Totally sort of complete directed graphs, it's quite clear that they give you bags in the sense that all permutations are allowed between your nodes, if that's how you want to understand bags in a particular context. And there are situations where you might want to mix things, and those mixes, you might have a good claim to have a sort of a data structure that is recovered. Like, in this particular case, actually, it's not clear to me that you would say that this is a bag that is sort of a source and the target is a single element. So you have a tuple of a 2 bag and a 1 element, because maybe for that you would require that all the elements in the bag are actual source nodes, and in this case only 1 is a source node. But anyway, the spirit is that there are clear cases in which just a subclass of spinal graphs give you faithfully the data structures that we are usually interested in. And so that kind of compels me to say, well, let's take spinal graphs in general as a object or a notion to encode these kinds of things. So I would repeat again, just for reference, that the perspective of permutations, which is what Nick and I had been considering most of the time, were for what we call hyperedge symmetry, which effectively just encodes what permutations are allowed between different elements. So it's the perspective that since we're going to declare our element, so basically our vertex names or vertex unique labels in a list, we were going to have to permute them in some particular way. So what is the redundancy between these, right? So that sort of structure will be given the analog of that sort of information. In this case, is the generation of either automorphism groups of your directed graphs, or perhaps more specifically path or homotopy groups or homotopy groupoids, or what people call path groupoids on these things, right? So just to say that there is well-defined symmetry structure that can be directly inferred from a spinal graph, but it's not explicitly encoded. So it's a similar notion to generators of of permutations, right? Like so far in the computational, we have implemented generators of permutations of given nodes in a particular edge. And so similarly, the spinal graph sort of generates all the possible sequential navigations of your nodes in particular. And you could generalize to say what are the bijections that are allowed and so on. And you could look at the automorphism group if you really want to, or sort of the sort of local automorphisms of the graphs and things like that. But that's sort of the idea. The idea is the spinal graph gives you a form of generalized generator for the internal relations between the nodes. And an important observation to sort of defend spinal graphs beyond permutations as an encoding of edge type is that, you know, you'd say, okay, so in the cycle case, in a back case, in this mixed case, they all seem to be, you know, reasonably well described by permutation generators, or just by the permutation picture, where you say, okay, cycle will be your list of nodes with the cyclic group action, with a sort of set 3 action, for example, as I say here. Can see myself, but yeah, as you can see on the screen. Similarly, you know, the bag that is full symmetric will have a S3 action, you know, the axonal elements, and maybe something that is mixed will have some partial set 2 action. You know, the set 2 action is restricted only to 2 elements, but you know, it's well defined there. So one of my sort of comments in defense of spinal graphs is that if you wanted to see the difference between a so actually. This, what was the thing that the diagram above? Oh no, sorry, it was the one on the whiteboard. So I'll just draw it here on top of this. If you can see this. So if you would like to see the difference between this ordered path graph and something that looks the same, so I'll just draw 3 nodes the same way, but where instead something like this. Right? So it's what people call a span, right? And you have two edges going in that direction. There is no permutation allowed between those. And that's a tree. So that's a data structure that you probably are interested in using in some implementation or in some context. But the permutation picture wouldn't allow you to distinguish those two, because in both cases, you're not allowed to make any exchanges of nodes, because exchanges of nodes essentially amount to cycles of in your directed graph, right? In embeddings of cyclic graphs, and so to speak. But nonetheless, you still have embeddings of path graphs, meaning you can still navigate your graph, your spinal graph, in certain ways. So anyway, that's kind of the other point why I have the faith deposited on spinal graphs to be sufficiently expressive beyond what we are currently thinking as lists and permutations. Yeah, any comments, questions here? Oops.
Yeah, to me, it does seem sufficient. I'm just thinking that directed case again. If one had like 3 sort of subgroupings of vertices, you could still represent that with a spinal graph. In that sort of each grouping could be, let's see. You know, one could think of like some sort of categorical label on the vertices, like some 0, 1, 2, or some natural number or whatever, some unique symbol. But is this directed spinal graph enough to sort of capture that? So yeah, take that directed case where one had sort of 3 groupings, and then there's some notion of directionality among the groupings themselves, which in a sense is, I mean, is that kind of, yeah, I mean, I like the ability to sort of represent hierarchical relations among the vertices also. I think that's quite useful.
Yeah, no, and that's an interesting question, actually. Let me give myself some real estate on the screen.
Mm-hmm.
Give me a sec. I'll just scroll down to white space. So there's something interesting here because, and this is one of the examples that Nick was suggesting to think about. So if you have something like this situation, right, where your back contains 4, let's call them 1, 2, 3, and 4 nodes. If you want to somehow represent a source and target situation, obviously there's more than one way that you can do this, right? That you can obviously just represent it in a way that, you know, all the possible directed edges that will imply that that 1 and 2 are sources and 3 and 4 are targets are drawn. And so maybe whatever the other edges that you find in this spinal graph, as long as you find that subgraph, it's basically singling out 1 and 2 as source and 3 and 4 as target, right? But what happens if I delete one? Oops. What happens if I delete? Can I? No, it doesn't allow me to. So if I delete one of the edges like that, right? It seems like there's still some sense in which 1 and 2 are sources and 3 and 4 are targets, but it's a different graph. And, you know, even if you define as source and target as the in degree and out degree 0, right? So 1 and 2 have in degree 0 and 3 and 4 have out degree 0. So that property is still maintained, right? But you no longer characterize that graph as source and target, right? So this is the thing, that there might be, because, you know, in a sense, if you want to think of 1 and 2 as being some kind of inputs and 3 and 4 being some kind of outputs, it seems that the 3 sees information from 1 and 2, but 4 only sees information from 1. If you're thinking of this as some kind of computational flow in some way, right? So maybe that just represents some kind of intermediate functional dependence. Like we are used to thinking, you know, a bunch of variables just map into a bunch of variables in terms of some kind of morphisms, right? But maybe that of a bunch of variables to a bunch of variables, right?
You cut out for about 5-6 seconds there, Carlos.
Oh yeah, sorry. Yeah, I got a note that my internet connection was unstable. So I was just saying that this might be a case where one can distinguish degrees of dependency in between your sources and targets, or your inputs and outputs, right? Like most of the time, you like to think of a set of inputs and a set of outputs as some kind of outer limbs of a black body, so some black box that mixes the inputs in some way and gives you an output, right? So these spinal graphs might give you a bit of a finer control on exactly what you want to assume that goes on inside, right? So if you draw a complete bipartite graph in your spinal graph, then that's going to mean that your inputs and outputs are fully mixed, right? There's no it's kind of implying that for all the possible inputs to the all possible outputs, for any given output, there's an influence potentially from all the inputs, right? For any given output, there will be an influence from all the possible inputs, right? It's not, you're not declaring anything because, these spinal graphs are not really computing anything themselves, right? They're just data structures. They're just holders of data. But in terms of a representation of a dependence for that data structure, that could be the granularity, right? That could be the expressive power that you want to say, as a whole, I have dependence of this whole bunch of nodes on this, and they give output to this whole bunch of other nodes. But it so happens that the specifics of which ones connect to which are kind of specific and possibly non-complete, right? So this one might connect to 4 or 5, this other to another set of 3 or 4 or whatever. Like, it might be more complicated, and only in this general. Mathematically, you might want to say generically, okay, I sort of blur the middle and just consider this as black box function from this number of variables to this number of variables, right? Oops. Right, it's that kind of simplification, but spinal graphs might allow you to be a little bit more expressive, and similarly with trees and so on. But I honestly think that, the other point of discussion that we had last time was, very related to this, actually. Let me just keep this on the screen for a second. The other point of discussion was, sorry, this probably was on the, maybe on the other document. But actually, it shows here this idea of nested structures within an edge, right? So let me actually just share the whiteboard because it's going to be much.
Yeah, it's whether you want to push those down to the spinal layer or delegate them to the I suppose upper layer where one has hyper edges. Yeah.
Precisely. Yeah. So that was exactly my point. The point was, okay, the hypergraph object, right? The hypergraph structure is exactly, in my opinion, what allows you to nest things effectively, right? If you want to consider like something that contains a bag inside, right? Like you have this kind of situation where you have 1, 2, and 3 as a directed edge, and then it goes into a directed edge. It's clear that at the bag level, you have a 2 bag that is a subset of or is contained in a 3 bag, right? So
but we don't have or don't want relations among hyper edges, because then it becomes kind of that meta graph thing, which where one because there's no indication that this 2 edge sort of belongs to that containing 3 edge. They're sort of separate.
Yes. However, you can the natural structure of bags sort of gives you the ability to define those kinds of things, because as bags, these you can just directly compare them sets, right? And in this way, you will be able to say that the 2 bag is contained in the 3 bag because there's just set inclusion. Right?
But I would never be able to say or indicate that a 3 bag belongs to a 3 bag, because they would just be equivalent, sort of on the same level. But if I wanted to say that, for whatever reason, that a 3 bag lived inside another 3 bag, I kind of can't do it. I'm sort of restricted from doing that.
Yeah. So you can't. So something that I think is worth mentioning at this point is that part of the flexibility of this perspective is this edge place idea that the sort of the edge structure is meant to be sort of minimal. Like we are not intending that spinal graphs, like just a directed graph, should do all the work. That's not the point of a spinal graph. Spinal graphs should do enough to recover what the usual or data structures of interest we want, and then the hypergraph is the sort of proper data structure that we want to manipulate. Like a hypergraph is the generalization of something like a data set. Like instead of your data set being a list of lists or something, or a list of numbers or something like that, or a table of numbers or whatever, we want hypergraphs to effectively replace those. I mean, hypergraphs recover all of those. So far, there hasn't been really a structure that cannot be adequately encapsulated by a hypergraph with this, as assuming that there's this degree of flexibility in edge types, right? And so you want to basically assume that your hypergraphs are going to articulate things like hierarchy, or whether things are inside other things, and things like that. But again, I insist there is a possibility that you just look at your edges as new nodes, because I think that's perfectly within scope of what we're trying to do here. And then you build hypergraphs on those new nodes. So effectively building hyper edges and so on, and sort of building edges on edges and things like that. But there's really no problem there. You can go there, but and you could even, it's kind of like when you do category theory, you can be doing one categories but also two categories, and the fact that you can do two categories doesn't really affect how you do one categories in a way. Like it informs it, or it clarifies some points or something, but it doesn't really change what is the natural way to do one categories. So this is similar in that respect, right? I mean, for those unfamiliar, just so the picture makes sense. So in category theory, you typically have this kind of situation where you have an object related to another object by a morphism, right? So a two category is a situation where you have similar things, right? But if you have two morphisms, F and G, there are sort of connecting the same two objects, then you can also get sort of a further morphism, call it phi, between the morphisms themselves, right? So it's a way to do morphisms between morphisms instead of morphisms between objects, and sort of n categories go all the way up, right? Like you have several such morphisms and morphisms between them, and the picture gets kind of complicated. You draw these kinds of things, then arrows to this, then arrows between those, then arrows between those, and so on, right? So that's something you can do, but the reason I'm mentioning this is that what you do at level 1, right, doesn't really influence, or it's not really influenced by what you do at level 2, level 3, etc. Right? It's just
it doesn't restrict you.
Exactly. So anyway, I think that's basically the recap that we are going to. So this was mostly about the canonicalization problem that we discussed last time. But this time, I much want to focus on what these spines are good for, because it seems that for canonicalization we have some issues to like do things effectively and to come up with good algorithms, which, I mean, in a way, by the way, this still is firmly in the vein of our previous techniques and things that are quite standard in hypergraphs, which consist in changing the edge information with a graph information. So maybe like replace an edge with a click, or replace an edge with a cluster, or a star, right? Where you create a new node in the place of the edge, or this edge place idea, and then you just connect the new node to all the incident nodes of that edge. But yeah, as I say today, I much rather focus on the good aspects spinal graphs, which are pattern matching and for rewriting and whatnot. So any comments, questions? I mean, I don't know if there's anyone in chat that wants to, ask something, clarify something. Otherwise, I'll move on to that point.
We have Sundar asked a question here in the chat. He said, you move up the categorical hierarchy by considering edges as objects and edges. Hyper edges between these edges.
Is that the comment?
Yeah, it's a question.
Yeah. So no, exactly. That's the analogy. So the analogy is you would consider edges between the edges, and whenever we say edge, we really mean hyper edge. So you could consider an edge as something that connects the graphs, and this is nothing too fancy, because we know that there are these equivalencies with graphs where you might replace all your edges with new nodes and then do sort of pairwise connections, basically what we could call an incidence graph of your hypergraph. And then you can just build a hypergraph on the newly created nodes, which will effectively amount to a set of edges on edges, and then you can keep going, right? So as long as you keep some labeling scheme, you actually can do this higher towers of meta hypergraphs, as you want to call it, really only with the labeled graph structure, not even the hypergraph structure. So there's no sense in which we are somehow going into some psychedelic territory where it's hard to imagine what kind of objects you have, and that's partially the reason why I'm not that interested in going first to higher and seeing what operations are natural in sort of towers of n hypergraphs or anything like that, because I actually think that we don't have a good base. It's not like when people developed higher category theory, ordinary category theory was very well studied and well developed. There was a lot of machinery and results and folklore that was very well established there, but we don't have the analog for just hypergraphs, right? We are still trying to have a cohesive data structure that is flexible enough to account for all the stuff that people do, and that serves the purposes that we have, which are somehow in 2 or 3 different directions that are not very collinear in a sense. Like we are trying to, on the one hand, do, for example, network analysis, where you use your hypergraphs as models of reality, models of complex systems, models of networked interactions and things like that. That requires much more sort of statistical analysis and the analog of principal component analysis and eigenproblem kind of analysis and so on. Then you have the application for generative systems, which is more in the line of the physics project, and where you're using your hypergraphs as sort of the substrate for automata kind of productivity and things like that. And so you want them to be considered as objects that are intrinsically expressive, that they contain some intrinsic information and not just some statistical distillment of a real system. And then you have another direction, which is the symbolic calculus kind of direction, or the diagrammatic calculus sort of direction, which is where I was coming from originally, with all these questions about higher algebra and higher compositional structures and so on. So it is a challenge to have an object, a data structure, and a framework that can sort of parsimoniously be useful in all these different directions. And of course, we have the very real examples of packages out there that are specialized for certain kinds of applications, but don't do a good job at just using hypergraphs as a framework for computing, and instead kind of give you a very specialized hypergraph object that you can use for specific applications. So for example, if you're interested in statistics of complex systems and complex networks, there are good Python packages that allow you to compute fairly large data sets and compute hypergraph metrics on them, like centrality measures and degree distributions and things like that in a fairly efficient manner. But those packages will be completely helpless when you try to do something like generalized matrix algebra when you're trying to use your hypergraphs and rewriting to express some formal systems, or to do generative models where you're using the rewrite rules to sort of generate larger and larger hypergraphs. Those packages are useless for those things, right? They're useful to, given a generated model, analyze the single steps of the generated model, but they're useless to actually generate the states and so on. So anyway, just to give a perspective, that what we're trying to do here is non-trivial. Like, it has some well-documented difficulty for the flexibility of the objects and so on. But that's why I thought it would be important to sort of go back to the drawing board, quite literally here, and just try to be on the same page of what things mean and what are the ideas that are the foundation of these objects. So let me see. I had, yeah. So the other thing that I want to mention today was just wanted to give a sort of flavor of what I think these spinal graphs are good for. And for this, I will transition into drawing mode. So I'll just turn off my camera because of sort of the precision of my screen. So the idea with, for example, if we do rewriting, so let's do rewriting. Oh no, I have such laggy screen again. This is not going to work, I don't think. That's a bit better. So rewriting with the spinal graphs, if you think about how you would encode it, right now, if you were to write a, just define a rewrite rule, something like this. For instance, the input might be an undirected ternary edge, and the output, so obviously the pattern matching recognizes the locations 1, 2, 3. So these are identified nodes, and you might want the output to be, for example, directed edge here and 2 undirected edges here, and unary edge here. Whatever, some weird rule, right? If you wanted to implement this, you would have to keep track that here your symmetry type is undirected. Similarly, here your symmetry type is directed. Here is undirected. And here it doesn't matter, but let's say it's undirected. So these would have to be tags that at the level of implementation you need to do rewriting of those on top of things, right? Like you need to be saying, okay, so here I mean, perhaps this is more obvious if you consider an even simpler example where imagine what happens when you change from, say, find a directed edge and just output an undirected edge between those, right? That's even a sort of more minimal example of what I'm trying to say. So here, that is somehow tracked in our data structure as directed. And this is somehow tracked as undirected. So the advantage of having a spine encoding of symmetry is that, you know, the way you would look at this particular rewrite rule would be have two edges. I am saying that there should be a bag between them. And I'm going to rewrite to something where the two edges are again in a bag. Okay, no problem. And then, but if this is directed in this way, then you just write the spine for that directedness, which is that edge. And then if this is going to be undirected here, I just write the spine for that bag, which is, for example, I mean, no directed edges or the fully connected directed graph, depending on interpretation that we agreed on. But in any case, this is an operation that is just doing graph rewriting fundamentally, right? It's just sort of highlighting subsets. So it's doing pattern matching with subsets and then doing pattern matching with graphs, right? Because when you go on your actual graph where you would apply this rule, right, you have things like this. So pattern matching will look like, oh, here's a bag. You know, here's a two bag that you can match. And then if you match it that way, you're gonna rewrite it on that same thing with your two directed edges. So that edge becomes undirected. Sorry, these are all directed first somehow. Right. So the point here being that you don't need to track anything other than pure graph rewriting in doing general rewriting for edges with spinal graphs. And you need to be able to pattern match bags, but once you've pattern matched a bag, all you have to do is to find the graph, the spinal graph isomorphism inside the bag, right? And of course, there, you know, bags and spinal graphs are connected, so they are not, you know, if you have two directed edges here and you have a multigraph, right? That situation will look like, you know, if we zoom in into that situation, that looks like this, right? Where you have two edges. It looks like there are two bags in this way. If the lag allows. Actually, maybe this doesn't make a lot of sense. Makes more sense to yeah, just highlight with this kind of bag and then highlight this kind of bag, right? So this is how you would treat those two situations, well, technically with directed edges like that. So your hypergraph will be, will contain highlighted, oops. It will contain highlighted two bags, right? Like this will be a two bag. This will be a two bag. This will be a two bag. There'll be two bags here. There'll be a two bag here. There'll be a two bag there. So this is what you could call the sort of the bond hypergraph. This is the sort of the, which is just a subset of the power set, right? It's just a collection of subsets of your, or perhaps a multi subset of the power set of your nodes. And then, so you first pattern match with the bags, and then once you've done the pattern matching with the bags, then all you have to check is the spinal graph pattern matching within that bag, right? Which is, it's just going to be some graph isomorphism problem restricted to the subgraph of the bag, right? And so, yeah, that's kind of the, like, if you have a pattern that is a little bit more complicated, so you actually have a hypergraph, imagine that you have something that looks like this, what I normally call a lollipop, that has a binary edge with some higher arity edge. Then there's two layers to this. I imagine that there's directedness here, and this might be cyclic, right? You're first looking at a sort of the bag version, which just looks like, same nodes, but only with this kind of thing. Maybe that kind of thing, right? Where you have the three things, and so you do pattern matching with the bags first, and whenever you have bag pattern matching in an actual hypergraph that over here, that has whatever many nodes. Maybe here you have this, and maybe you have this, right? You can similarly sort of project down to bag, and in bag, let's see if we can do this. Right, I get the same thing, but now without these edges, and instead I get some kind of you have this connected, you have this, and you have this. You have this, you have this, right? So you first do a bag pattern matching, right? And all, you just need to, so it's important that your pattern matching at the level of bags is efficient. So this is, we implement a good subset pattern matching, which I don't think it's, that difficult. Is probably already quite easily available in the language. And then within those, once you've done you found a pattern match in your hypergraph, then all you have to do is to actually find the internal composition of the spinal graphs, right? So you can, how to express this? So should have probably move this. Let me just do it like this. This is bag. This will be spine. So in spine, you would find this here and this here. And remember that these are labeled according to the bags, right? So this bag we're calling A, is B. This is label A, and this is label B, B, B. Right, just to be sure. And yeah, all you have to do here now is, I call this bag here. I'm going to call this spine over here. So it's just the same thing, as you can imagine. Actually, thrown some things here. Maybe that, that, and the spine just looked like this. Right, so that's basically the idea here, that in your pattern matching, any pattern has a back pattern and a spine pattern associated to it, and you would first scan for bags. Once you have a bag match, then every bag will have a spine inside. So you go inside, you try to match for the spine. If you do, you have a full match. If you don't, you keep going. Right? That's basically the idea. And of course, the advantage of this is that once you rewrite, not only for pattern matching, or sub hypergraph identification, but is that when you write a new edge, the way you specify the new structure is just by writing a graph on that position. Exactly, right? Like just writing a spinal graph in that position. So we are firmly within a very well understood realm of rewriting, right? We don't have to, if we learned anything from Nicholas Baer and all this work about categorical rewriting, is that when your categories of hypergraphs are, get more, how to say, they get more baroque in some way, right? They get a bit more sophisticated. You start to lose expressive. You start to lose axioms in your categories, and you things become less clear. How you you start to lose certainty in terms of what categorical structure exactly you have. So the advantage of this is that my claim, and again, I still have to be shown the correct in this, and I still need to prove that this is actually implementable and useful. But the claim here is, or the promise is, that we could be expressing all kinds of data structures on edges, or at least the wide variety of things that we are interested in, like trees and cycles and tuples and bags and whatnot, simply by reducing to doing rewriting on subsets, sets of subsets, or multi-sets of subsets, i.e. Unordered, undirected hypergraphs, and directed graphs, right? So it's sort of reducing a very big problem and sort of unknown sort of unknowingly big problem of generalized hypergraph symmetry, pattern matching, and rewriting to what I think is a fairly simple combination of undirected hypergraph rewriting and directed graph rewriting, both of which are very well understood in the literature, and we have good mathematical theory to build on. You know, and of course, the entire advantage here will come from having the ability to use labels and to keep track of labels and use these hypergraphs as supports for data that we are manipulating computationally and we are sort of operating with instead of operating about or computing about, right? Like that's kind of the end goal here, to have a computation, sort of a hypergraph computer in a way, instead of just a way to understand or parse hypergraphs. So anyway, that's kind of the promise here. That's why one of the main advantages of this, that it is very rewrite friendly, and it's very and it allows to reduce the general problem of hypergraph isomorphism as a general type, hypergraph isomorphism, hypergraph pattern matching, hypergraph rewriting, all these things to sort of a two-staged process where you first do a bag analysis or a bag pass, and then on each bag you just do directed graph analysis. So each of these two steps we have very powerful functionality for, and therefore I think are quite safe there. And just as a final note, for anyone in the audience who knows about this, spinal graphs are also interesting because they give us a well-defined combinatorial species. So spinal graphs are a well-defined combinatorial species. So that means that you can rely on generating function kind of mathematics and magic, sort of the combinatorics magic, to solve counting problems for these kinds of things, and have fairly powerful theorems that tell you things about what it means to sort of put together several graphs or count numbers of graphs. And there's like this very neat interpretation of sort of a calculus of shapes, or a calculus of forms in this the discrete combinatorial sense. And directed graphs with these specifications are, you know, bags with a spinal graph assigned to it and so on. And these hypergraphs just give a very well-defined combinatorial species. It's no longer, like, it was a bit mysterious to me what even the category of these things that were going to be before, when you just haven't, it was clear to me that it was something like a bag, meaning that every edge can be projected down to only its node components. But it was not clear at all to me what was the mathematical object that I had to specify between those nodes. Like, what was the datum that I had to give to sort of substantiate an edge, right? It was clear that if I wanted something like a tuple, then it would be enough to give an ordered list of nodes or something like that. It was clear that if I wanted something like a bag, it would be enough to give a set. But in general, the intermediate states, they all felt like I needed a very case-specific implementation. And this directed graph business with spinal graphs seems to give a pretty parsimonious thing that has all these mathematical niceties about them. So they are kind of, the summary of all this, by the way, is that they are very ready to compute. they are sort of out of the box, ready to compute. We have good functions in the language to compute with them, and we have very good mathematical theory to go on in a more formal sense. So yeah, anyway, that's kind of the slogan. And oops. Hey, can you hear me?
Yep. Hey, just doing
Yeah,
a quick
sorry.
sound check. I think we've got maybe 10 more minutes.
Yeah. No, I was just my screen blacked out for a second. Let me stop sharing.
Sundar says, thanks for the enlightening lecture.
Who says that?
Sundar in the chat.
Yeah, no, appreciate it. I can show my video again. Sorry, Richard's saying, this kind of tiered filtering is what happens in normal rewriting. You filter by arity first before filtering by connectivity. So adding another tier to these filters is adding more pruning control to the pattern matching process. Yeah, I would. Yes. This is true, but at the same time, the more than tiered filtering, you could imagine that before, how to express, so before it wasn't clear that in order to pattern match something like an undirected edge, it wasn't obvious that you would have exactly one bit of data that was the undirected edge. It might be that you needed to have all the permutations of that, of the names of the, stored in the n factorial lists of the node names, and then you would have to pattern match with the same kind of structure at every edge of your hypergraph, which is a very explosive amount of information.
Yeah, I've done it by accident, or when I was experimenting with implementing these things in Wolfram language, I did the undirected case, and it's it's huge compared to the directed case.
Exactly. Yeah. So that's a big. Thanks for that comment, Richard, because that's a big motivation for what we're doing. Is that we're trying to reduce the combinatorial explosion by encoding internal symmetry patterns. So basically, the reason why you have a combinatorial explosion is not that an undirected edge has a lot of information, because in a sense it has less information than a directed edge, right?
Yeah.
But because you insist that you must represent your undirected edge as a list, right? If your primitive object is a list, then definitely you're going to have to somehow encode the permutations that are allowed for that list to represent the same object computationally, right? So that's where you get the combinatorial explosion. But if your primitive object is no longer a list, which is something I should have said more at the set out of my explanation, is that here we're really trying to imply that bags and spinal graphs are the foundation of the computational objects, right? Like even at the implementation level, if we want to think that all you need is an alphabet of symbols that you are going to, which could be like Boolean zeros and ones or whatever, some kind of distinguishable discrete data pieces that you can populate your node or memory locations with, and graphic structures that are directed graphs and sets of nodes, right? Just
can I pick up on that actually, because you just mentioned like kind of categorical labels on vertices. Some wild people introduced this notion of bidirectionality, and it's, to me it seems like directionality is in a sense sort of arbitrary. Like it makes sense for like information flow, like flow problems, I don't know, but it's really just some set, like whether we're going from A to B or B to A is just some element of a set, right? It doesn't or like, for example, you had this directed label that you put in quotes as a string or something, just to indicate that this edge was an undirected edge, this was a directed edge. yeah, to me, it seems like there should be some sort of freedom in that. Like, so for most cases, for most things we're doing, it's clearer to draw an arrow and call it directionality, but really, could be anything. I mean, it could be color, it could be whatever.
Yeah.
So like like you have undirected, you have directed, you have mixed, and there's also this bidirected case, which, as I said, yeah, in the sort of graph literature, people do it. I don't know why really, but it's like for some reason, some people want that freedom to express this extra edge type. Yeah. So
No,
what are your thoughts on that?
That's good news, and I would say like that aligns with. I mean, it's good news to see that other people are considering that, because that's, to me, that sounds a lot like undirected is lack of connectivity information. Directed is connectivity information in one direction, and bidirected is the presence of directional connectivity in both directions, right?
In both, yeah.
So that's exactly the ABC cases that I was highlighting before as, at first we were a little bit, should we have undirected and directed, because we are just kind of biased to come from a framework where you only distinguish between those two, maybe because our data structures kind of prompted us to be more thinking in those two terms. But it might well be that, I mean, if we take the spinal graphs more seriously, if you were to believe, you don't have to be sold on them, but if you just assume for a second that they are the efficient way to do all these data structures, then they have their own sort of language, right? And lack of connectivity is different from full connectivity, although for a human user, those might be indistinguishable in some situations, right? The fact that you can, if you give me a vertex with two dangling or a bunch of dangling vertices connected with edges, I think indirectly as, I could move this around. If you give me like a physical, it's like, this magnet toys that have like metal balls and rods, like this, whatever they're called, this kind of toys that you can move your edges around. So there's obviously a sense in which these are not rigid, but the moment you put some rigidity on the other rods, then the thing can only sort of like rotate together. So it's okay. Let me see this bidirected graph.
Yeah.
Definition.
In a sense, it's like I bring this up that we either sort of reject it or, we encompass it somehow. Forget the half edges. I think I brought them up one time in a conversation with Jonathan and Stephen, but I forget how that went. But here they've got this. I mean, there are sort of two types of bidirected edge: this extroverted and introverted. And how does this apply to like the higher ordered case that where like three edges? And so anyway, I was just typing a comment. My comment was extroverted, introverted edges to me suggest that this link notion, the relation between vertex and edge, I say should, but what I mean is could carry some information. But yeah, whether it's like obviously something as simplistic as possible is the simple and universal. But can you kind of maximize both? I don't know.
Yeah. No, that's definitely part of our thinking here, or should be, I should say.
Definitely, yeah, I agree.
Yeah. But at the same time, there's also a very practical aspect of this, and Nick and I were thinking about this last week on how to. At the end of the day, we want a canonicalization algorithm for arbitrary hypergraphs. That's sort of the holy grail of this whole thing. Like if we can get that, then we're good, right? Because the whole problem is we don't have good algorithms that mix edge types, mix undirected with directed, or multi edges even are kind of problematic for canonicalization and things like that. So this is an effort overall to get closer to that notion of so if we like how these edges are doing the job. And by the way, just as a final thing to show, before we run out of time, there was this extra bit of justification for spinal graphs, which has to do with hypergraphs as data structures, exactly as you were saying, Richard, which I need to always insist that what confers hypergraphs their data structure expressive power is labeling. So hypergraphs alone are just topological kind of statements, and they just represent some connectivity pattern. But in order to have data proper, you should assume that there are labeled symbols, so label symbols that are carried by the memory locations of your data structure. And by default, you can assume that you are unlabeled, but what that really secretly means is that you are labeled by unique labels that you're going to keep track of, right? And maybe also the fact that you're going to be simple in the hypergraph sense. So
here you only show labels on vertices, and is that a?
Yeah. I'm only showing labels on vertices just for simplicity, but if you see some, like I just said, if you see some element that is like distinct on both at the implementation and the graphics sense, that should carry like a unique label that is like identifying it. So here the point I'm making is that when you wanted to think of hypergraphs as lists of symbols or lists of symbols, there was going to be a redundancy when you consider loops, right? So this thing is looped here in this thing, or these things are looped in. So this particular hypergraph has a one occurring twice here and has a one occurring once here. So when you want to give unique IDs to nodes that are meant to have unique IDs at the implementation level, but you want to represent the same data as you had here, you necessarily have to do a labeling scheme. And so because you had this degeneracy, so to speak, this multiplicity of an edge, you have two options, right? If you just sort of do a normal ordering and you give unique names as they appear. So one, then you run off all the names that you already have, 1, 2, 3, 4, 5, and then you use the next one, 6. Then you essentially, for this third edge, you have two options. You can either write 251 or 256 because you didn't know where you came from, right? Both were 1 in the original. So the interesting thing is that if you do that, but you on top of it keep the information that the labels need to represent the original degeneracy of data, meaning whatever thing gets expressed by 1 originally, which in disguise was not a unique ID, but a label, then now you're assigned to 6. And the interesting thing is that obviously, because that's what you're labeling, these two things are going to be the same, and you just can show that these are two hypergraphs with different vertex names but different labels. Different vertex names but same labels. But when they are shown as hypergraph structures, they are the same. These are the two identical hypergraphs. And so
okay, we need to wrap up in a minute.
Yeah. So the punchline here is for Richard to keep in mind that another good aspect of spinal graphs is that you will not be able to, if you represent the spinal graph on 2 nodes, right? That's a 2-node graph, whatever it is. That's clearly not going to be identifiable with a 3-node graph in any way, right? Because it's just, isomorphism will never work on a different number of nodes, just in the first check. So that's yet another point in favor of spinal graphs. And if anyone is worried that you might not be able to represent loops, fear not. I'm still insisting on how labels are the important part to do with hypergraphs, to compute with hypergraphs, because you can just take your ternary edge and just label it properly, and this is the actual data structure. You have 1 and 2 twos, but you have 3 nodes. Right? That's important. So yeah.
Cool. Okay, that was a nice comprehensive session. Really appreciate it. Thanks for whoever that joined in the chat. I really enjoyed that. So okay, we'll catch you next week. There's no additional live stream scheduled for this week unless we do a surprise one, but we'll let you know in the Discord. Okay.
Absolutely.
Bye for now.
Thanks very much, everyone.
Cheers, everyone.
Bye.
Bye.